Hello, so today we're going to be looking at this reaction right here. So thallium is being oxidized and cerium is being reduced. This reaction is fairly slow though. It's pretty slow under normal conditions. However, if we add a catalyst, we will have this mechanism right here, which is a lot more favorable, and we will have this rate law. So let's take a look. So let's uh, Let's identify all the components here. So the cerium and the thallium here are the reactants. The cerium and the thallium here are the products. So what about all of the different manganese though? We see in the first step, we are consuming manganese, but then in the end step, we are producing it again. So the concentration of manganese stays, well, it is conserved through the reaction. So that means manganese 2 plus is our catalyst. It takes part of the mechanism, but it's reproduced in the end. It isn't consumed. So now let's take a look at manganese 3 plus. We see that we make it in the first step, and then it's consumed in the second step. So this would be an intermediate. It's produced, but then it's consumed in a subsequent step. So it will be gone by the time the reaction finishes. And same with manganese 4 plus, created in the second step, consumed in the third step. So now that we've identified what each of these components is, what about we take a look at this rate? The rate depends on the concentration of cerium 4 plus and manganese 2 plus. So which step is rate determining? Well, we see here in the first step, we have one molecule of cerium 4 plus colliding with one molecule of manganese 2 plus and reacting. That would give us this rate law here. So that means that the very first step is the slow step. So let's compare these two mechanisms. So why is the reaction so slow under normal conditions, but a lot faster when it's catalyzed? Well, so you see here we have 3 molecules reacting here. And a termomolecular collision is very slow. It's pretty rare to see 3 molecules colliding in the correct orientation. However, as we see in this mechanism, every step involves only a bimolecular collision. And it's fairly common to see 2 molecules colliding. And there are plenty of collisions with the right orientation. So bimolecular collisions are a lot more favorable than termomolecular collisions. So what kind of catalyst would manganese 2 plus be in this scenario? Well, we see that these are all ions, so we would assume that this is an aqueous solution. And manganese 2 plus is also an ion, so that means it would also be an aqueous solution. So they're all in the same phase. They're all aqueous ions. So that means that this would be a homogeneous catalyst.